So on this drawing, I think the thing to realize is that, first off, how many different origins of replication do you have here? Okay, so I would say each one of these spots right there and right there and right there would all represent origins of replication. And if you go to the right and you go to the left here, it's kind of like you're opening it up, right? Do you see what's different between the top and the bottom picture? It seemingly is just opened up more. Now, in blue, I'm going to label out the original parental strand. And then I'll use a different color, like red. And I'm just going to go over simply the pieces that are being made anew. So in red, you have the pieces that would belong to the daughter strand. The reason this picture is good is because you can see, and it's maybe a little hard to see, but in those bubbles you have these little arrows that are going both to the left and right. And as they go to the left and right, you're seeing that replication bubble open up even more so. Now, as you can understand, eventually these two arrows will meet, and at that time you'll have the completed strand. You should have two of them. Cool. So you have all these replication forks, and they eventually meet up, and then we're essentially done with the process. Cool? So I think we're totally perfect. We love this part. Agreed? Okay, awesome. So I think we could say that maybe as far as some vocab goes, and knowing some of our major players of this, I think we would want to know for sure that you've got a replication fork, which is simply the Y-shaped region. Where DNA strands are elongating. The Y-shaped region where DNA strands are going to elongate. Replication fork. Oh, my bad. Still zoomed in. I apologize. Replication fork. No, fork. Fork. That looks really weird. That is how you spell fork, though. Does it really? Better? No, it just looks disproportionate. No, fork. We don't need a fork. This isn't a battle here. This is just, we need a fork. Let me show you what that is. Let's go back to this drawing real quick. I would say that this area right here that I've gone over in yellow, that would be a replication fork. So my RF, it's F as in fork. RF. Or fort, fine, we'll call it a replication fort from this point onward.
On that the top row, is that one on the right? Is that the same thing?
This right here?
Yeah.
Yes. It's an RF as well. And so you elongate the DNA, you add to each complementary strand, you add to the blue strands the new red one, until your replication forks meet up and you're done. Right? Okay, we also need to know some other enzymes that are important at this, or in this time. So I'm going to go over a couple of different enzymes. So some of the major enzymes. First major one is going to be helicase. which is the enzyme untwist the double helix. So if you will, they take your double helix, which is, like a wound upon itself, and make it straight. There's also another enzyme called topoisomerase. They prevent areas ahead of the replication fork. That's fork. From overwinding. If you unwind a cord, like the 5 feet in front of you, you know how like beyond that point it's all wound up. If you think about it, so this is going to prevent like overwinding in an area that may be a little distant from the replication fork. And there's also another protein called a single strand. It's actually an enzyme. Single strand binding protein. And its purpose is to bind and stabilize the DNA and will prevent rewinding of the strand. Topoisomerase and SSBP, as it's sometimes called, have very similar functions. But topoisomerase is usually up ahead of the replication fork by some distance, and single-strand binding protein is usually very close ahead. Okay. So let me show you this picture real quick. You'll see on this picture, which of course is in your book, your replication fork is right here, correct? And it's going, do you think we're writing new DNA to the left or to the right? Yeah, we're opening up the bubble, if you will, right here, right? This is the replication fork. So we're going to the left. So you'll see topoisomerase is way up ahead, but what did topoisomerase do? Prevent areas ahead from winding up or getting too wound. Then there's SSBP, which does what? Keeps it stable, right? And then helicase, which is basically unwinding and also unzipping, if you will. Breaking these bonds right through there. And then we didn't talk about primase and the reason that we would add an RNA primer. Okay, so let's talk about some major issues with some of our other major enzymes. And probably the ultimate enzyme for today that you would probably want to leave with for sure is the enzyme called or named DNA polymerase. DNA polymerase. This is the major enzyme of replication. It is responsible for adding new bases or new nucleotides